Multifunctional material exhibits interaction between physical properties such as electrical, magnetic, mathematical, optical, and thermal properties. In the starting of 1980s, a class of multifunctional material has been discovered. It is important to create mathematical models to use them effectively in engineering applications. This model should capture the hysteresis phenomenon and the coupling behavior of the materials and be compatible with the laws of thermodynamics. In 2013, Crazy, Davino, Viswane, they developed a mathematical model, but due to the nonlinear nature of the model, until today, no one has been able to estimate the unknown parameters of the model to fit the data. To solve this problem, we developed a constrained nonlinear optimization problem techniques and statistical techniques. In 2019, Clemente Davino Viswane collected the data by measuring a galvanal rod, and they measured magnetization and strain epsilon for the different values of magnetic field H and stress sigma. So we have 200K of sigma, H, epsilon, and M measurements. The main difficulty of the problem is the model equations are highly nonlinear, and they are in terms of double integral operators, Price hysteresis operator, and Price stress function. Here, the input itself is the product of a nonlinear function f of sigma and the magnetic field H. The hysteresis memory evolutions made the problem more complex. It has both forgetting and remembering properties of the memory. Two inputs, sigma of t and h of t, creates the input for the hysteretic neural network v of t, which is the product of a nonlinear function f of sigma and the magnetic field H. So each of the neurons encode the hysteresis memory, and the outputs are collected through two nonlinear operators. The hysteresis memory evolution equations leads to system of linear equations, and we can estimate the values of C1, C2 by solving the system of linear equations, and we can set a range for the possible values of C1 and C2 by solving a set of system of linear equations and constructing the confidence interval for C1 and C2. We can estimate the weight omega by solving constrained nonlinear optimization problem using alternative direction method of multipliers. So in the results, we included the confidence interval for C1, and we also included the confidence interval for C2. And we also included three figures for three different values of sigma. And here the red line represents the fitted value and the blue line represents the actual data. So in this work, we have developed a novel two-step linear parameter estimation scheme for highly nonlinear model for multifunctional materials. And this model is general. So it is applicable for magnetostrictive, electrostrictive, and piezoelectric materials. So in future, we'll do cross-validation for selection of optimal parameters for a given function f of sigma. And we'll also make model selection with different choices of functions f of sigma.